Welcome to the BSM2 session, and I will just briefly remind you about how we plan for this session. With this asynchronous talk format, in this session, we'll have each speaker give a brief introduction to themselves and 1 to 2 minutes introduction of their talk or highlights of their talk. Afterwards, we'll ask the questions to the speakers, and you, throughout all the time, you can type your questions in Slack or in this webinar system and tell us which speaker you want to ask. We'll find the appropriate time to ask the speakers your question. Okay. Without further delay, let's begin our session. The organizer, would you please move Matthew McCullough to the panelist? Due to some schedule conflict, we're going to, even though Matthew McCullough should be the fourth speaker here, but we will have him to talk first. Matthew, would you please unmute yourself and give a brief intro to yourself and a 1 to 2 minutes introduction to your highlights of your talk? Please go ahead. Yeah.
Okay. Yes. Thank you very much. And I'm sorry for this mix-up. It's a simple time zone thing with another talk about Higgs measurements at future circular colliders. I'm Matthew McCulloch. I'm a staff member at CERN, and I'm a theorist and a model builder who has a strong passion for thinking about the future. My talk was about Higgs measurements at future circular colliders, and I tried to highlight that when the end of the high LUMI LHC era has come to a close, that we will still not fully understand the properties of the Higgs boson, nor will we have measured them well in all of the corners that we should. It will never be truly certain that it's a standard model like Higgs, just with the high LUMI LHC alone. And I tried to make the case that with future circular colliders, we can close these loopholes. Important questions like what is the value of the Higgs self-coupling and have we probed it quantum mechanically can only be fully addressed with future circular colliders. And I'll leave it there to leave time for everyone else.
Great. Yeah, thanks Matthew for the nice intro. Yeah, please type your questions in the Slack channel or in this webinar system. Let me begin with one, Matthew. So it's very interesting for us to see the discussion beyond the Higgs self-coupling operator, C6, right? So you highlight another operator, which is the CFOX, which you call it oblique parameter for Higgs and affects how the Higgs moves. Yes. So my question is, we don't usually see this people discussing this operator, right? And that's why you point out that's an opportunity. But I want to understand first, their series only generates this operator, okay? So in many cases, we'll generate other operators which are much easier to observe. Two is, even if there's no series only generates this operator carries a certain level of information that others don't carry. Can you give another angle highlights about how special this operator is? Yeah.
Thanks for the question. So let me share my screen. Can I try and oh, that's okay. I can just say in words. So if you have my slides.
Yeah, they have your slides. Yeah.
Yeah. Okay. Okay, perfect. So if you go to the one before, just with a few before with the big picture, there's a sort of list of operators before the goat. So we never really discuss this operator because it doesn't exist in the Warsaw basis. Normally, we do a field redefinition and move it into other things like four-top operators and so on. I think it's perfectly fine. It's a perfectly physical thing to do. My concern with it is that you lose a sense about what could be going on in the UV. So for instance, when we talk about measuring four-top scalar operators, naively, we think that that's associated with physics in the top sector, whereas there could be physics in purely the Higgs sector that has nothing to do with fermions that generates this operator. So in the Warsaw basis, we sort of forget what we mean by Higgs physics in my mind, and we might associate four-top measurements with top physics, and that's not new physics in the top sector, and that's not necessarily the case. Are there UV completions that just generate this operator? If I was being a little bit like a car salesman, I would say yes. There are, if you just have a heavy Higgs doublet that kinetically mixes with the Higgs, if that's the leading thing, then you just generate this operator. However, to be realistic, I think, no, in general, there will be UV completions in any realistic UV completion that's motivated by something useful, then or something interesting, then you would generate more of this collection of operators, and this may not be the one that we have most sensitivity about. So I think in the majority of UV completions, the other operators are more important to measure. However, my last comment on that would be that I think it's very important at the moment that we are honest about what we know and what we don't know. And I think, so if we place too many of we've learned a lesson about placing too many priors of our own priors on nature. And this is an operator that, unless we've ever constrained it experimentally, we will never truly know. And so what if there's some BSM scenario that we haven't imagined, or there's some motivation for it that we haven't come up with yet that actually populates mostly this operator? It would be a terrible shame to miss that just because we decided that we have different priors. So I think it's important to highlight that it's there and that we need to probe it and be certain of what it could be, regardless of UV completions. But in the sorts of UV completions we're interested in, usually it will generate other operators. Does that answer? I think there was sort of a third part to your question, which I forget.
Yeah, I think you answered very comprehensively, and you made it clear why we haven't discussed this much before, but because it's hidden in the Wassel basis. But I also fully agree with you that in this basis is closer, make it more apparent of its Higgs connection, and we shall not put too much UV bias towards physics here.
I think so.
It's a very interesting point. Yeah.
I think so.
Yeah, it's very fun. Thanks. Yeah. Yeah. So I don't see other questions. But thanks again for your nice talk and the intro. People may post other questions in the Slack channel, but you can occasionally check there to see to communicate with people there. Okay.
Thanks,
yeah. Thanks, Matthew, again. Yeah. Now we can move on to our next speaker. Okay, sorry if I pronounce your name wrong. I'm sure I'm pronouncing it wrong. Viswajit Das, would you please start, give us a brief intro and highlights of your talk?
So my talk, my name is Viswajit Das. I'm a doctoral student at Institute of Physics, Bhubaneswar, India. So my talk is about WW Higgs production at bottom quark fusion at Hadron Collider. So here actually we study that what is the contribution of this process in bottom fusion channel. We are interested to probe this VVHH coupling, which only in this BB bar channel we can have this coupling WWHH, but not in the light quark channel. And we see how the cross section vary with changing the kappa value of that WWHH coupling. And also we study the polarization dependence of final state W plus W minus on total cross section. So we see that in longitudinal polarization there is a huge contribution. So that actually coming from the Goldstone mode. Goldstone mode actually represent the longitudinal polarization of W plus W minus vector boson, and they couple to the massive quark, and the coupling is proportional to the mass, and we have the top mediated diagram, so that's why you get larger contribution on that mode. So this is this is the main motivation and the findings in this project. So thanks.
Okay. Yeah, thanks for the nice intro and the highlights. Let me remind everyone, please type your questions here or on Slack. We will have organizers helping you to move the questions from Slack to here. And also for panelists, if you have any questions, you can just unmute yourself and ask questions. Okay. Let me ask one. It's very nice and impressive that you studied the WW Higgs production with NLO corrections from the BB process. So the purpose of this study, beyond the precision calculation, is you want to probe the VV Higgs vortex. Okay. So how does this process sensitivity compare to the other process, which is the VBF di-Higgs, which in principle is probing the same vortex and sounds like which doesn't need to rely on the B quark fraction of the proton. And would that channel be more sensitive?
Yeah. So in the BB, as I have discussed in motive. So should I share my screen?
Pardon me?
Hello. Should I share my screen?
PMS scale. Oh, okay.
Okay. So in the motivation, sorry.
Which slides do you want to go?
Slide number 3.
Slide number here. You mean this slide?
3. Yeah. So
okay.
Yeah, as you see in this vector boson fusion, so they are double Higgs production. So we have same vertex here, but your point is that this WW Higgs 6 or ZZ Higgs 6, they cannot be separable. There are many BSM model which predict that they are not related, but in standard model they are related. So our motivation is to measure them or probe them separately. Here the bound of the on the kappa value is good, but the thing is that this vertex BVHH vertex they came actually from the WW Higgs 6 as well as the ZZ Higgs 6. And the next yeah. So in this double Higgs production with one vector boson, so here one can have them separately, this WW Higgs 6 or ZZ Higgs 6, but the bound is quite weak. It's from -9 to 11. So then our process this VVH, which can probe them separately, and we try to give them bound. Give bound on this VVHH coupling.
Okay, thanks. So now let's move on to our next speaker. Next speaker is David. He will give us a brief intro to himself and also talk about electron Yukawas, mass channel resonant Higgs production and FCCE.
Yeah. Yes, hello, can you hear me?
Yes, I can hear you.
You disable screen sharing, so I cannot share my slide. I just wanted to show the conclusion slide and summarize it in 1 minute so that people are, but I cannot do screen sharing, is that correct?
They can go to the slides, yeah.
Okay, this is the last one. Okay, very good. So I'm David Enterria. I'm senior scientist at CERN. I'm experimentalist. I'm working in CMS and FCCE. And here the idea we've been working a few years is to try to see if we can observe the resonant X-channel Higgs production in E+ and minus collisions at the Higgs pole mass. So this diagram there, E+ and minus going to Higgs, and then Higgs going to anything. Well, anything is not everything, but 10 channels in particular that are visible. Of course, this cross-section has tiny, this process has tiny cross-sections, and taking into account ISR and a beam energy spread of 4 MeV equal to the width of the Higgs boson, we expect 290 attobarns. And of course, we need to know very precisely the center, where the Higgs mass is. In principle, we should get 3.5 MeV at the FCC by through previous runs. And what we did then is to look at the at 10 channels for signals and backgrounds. Backgrounds are huge, 10 to the 3, 10 to the 5, 10 to the up to 10 to the 8 times larger than the signal. So it's a very challenging measurement also. And after doing the analysis with multivariate studies, we determined that the most significant challenges are Higgs to glue and Higgs to WW star lepton plus jets. And in this case, if we integrate an inverse autobarn and we have a beam energy spread corresponding to 4 MeV, the Higgs width, we expect a significance of 1.3 sigma per year and per IP. If you want to translate this into the upper limits, is 2.6 times the standard model value at 95% confidence level. And of course, this is per IP and per year. So the more IPs, the more years, we can reach a value which is close to the standard model. And this is a unique case, a physics case, because LHC, high lume LHC will get to 100 times limits of the electron Yukawa, and the FCCHA is 30 times. So the only way to really probe the coupling of the Higgs boson to the electron, which is at the end of the day one of the key ingredients of the visible universe, so will be by trying out this measurement at the FCC-EE. And just by having these 2.6 times the standard model at 95% confidence level, just with one IP and 1 year, we should be pushing BSM effects impacting the Yukawa, electron Yukawa above 100 TeV. So that's a summary. I'm happy to hear your questions.
Okay. Yeah, thanks, David, for the nice summary. I see questions from the audience. Let me begin with one. So obviously we all know it's very hard to measure the electron Yukawa, and that's why this study is very impressive that we can have access to it. Obviously, as you mentioned here, we need to, since it's a very low cross section, we need to know exactly where the Higgs is. So you said we need to run Higgs, no Higgs mass within 3.5 MeV through HZ running at 240 GeV. My question is about what's the 217 GeV thing? Is that the threshold scan? Would that help us determine Higgs mass more precise? And I haven't heard about this run at 217. Can you elaborate on that?
Yes, if you go to slide 20, you have there a study we did also in parallel. So the idea is to combine the next one. The idea is to look at to combine two measurements. So the standard way to determine the mass is through the recoil mass in Higgs Slalom. But if you run below threshold, it's that's the one before, slide 20. The slide before. If you take a look at this, is the line shape of the cross section of function of square root of S. So you see there is a point where this derivative is maximum, and this corresponds to the point where that is more sensitive to the mass. So the cross section is more sensitive to the mass. So this is very similar to the measurement of the W mass through E plus E minus going to WW. So here's the same idea: E plus E minus going to Higgs plus Z. And there is a sweet spot at 217 GeV that is maximal. It has maximum sensitivity to the Higgs mass. So the study that was carried out indicated that we can reach with 5 inverse autobarn at 217. We can determine the mass to within 5 MeV. Now, if we combine this with the cross section with the recoil mass in Higgs Slalom, which is the other method that gives you usually 5 MeV. So then we should know the Higgs mass to within 3.5 MeV. And of course, I mean, it's then the other good thing about the FCCE is that we will know the center of mass very accurately. So in a way, the idea would be to try to steer both beams at say 125.000 or 001, whatever it is, the maximum of the cross section. But in reality, of course, you have a beam energy spread, but we can control this. So we know exactly which part of the line shape of the bright Wigner we are probing at any moment. And then we accumulate events of different topologies, 10 different topologies. And after some time, we expect to see a tiny excess with respect to the backgrounds. That's an indication of the Higgs production there.
Yeah. Thanks for clarifying this. Yeah, it's very nice. Okay. I don't see further questions at this point. We can move on to our next speaker. will be from Luca Franco. Would you please give a brief intro to yourself and the highlights of your talk? Please go ahead.
Yes, can you hear me?
Yeah, we can hear you, yes.
So, yeah, my name is Luca. I'm a PhD student at Lab Pancy in France. My talk is an overview of many results obtained by the Atlas collaboration using LHC-RAN2 data, which means proton-proton collision at the center of mass energy of 13 TeV. So these were measurements of the Higgs boson properties, mainly performed in the bosonic decay channels, and also their combinations and interpretations.
Yeah, thanks, Luca, for the nice intro. I see any questions? Yeah, go ahead.
Yeah,
please go ahead.
17. I think it was. Yeah, 17. It's where they're talking about Higgs constraints on kappa lambda.
Yeah.
So in kind of the middle plot with the different kappa lambdas, you can see that you have different invariant mass distributions. So that gives you a lot of constraint on kappa lambda. But when I look at the upper plot, really looks like this is just a cross-section measurement and putting bound on kappa lambda. So do you know if the changes in the kinematic distributions were accounted for different variations in the trilinear coupling?
Yeah, so basically this plot in the middle of the slide, it's just the you see there is a vertical line which defines these two low mass and high mass regions. So you see in the low mass there is this there is some difference between the distributions of the mass between different hypotheses. So this analysis mainly had two goals. One is to use the non-resonant production, which is the Feynman diagram on the bottom left part of the slides, to put a limit on the trilinear coupling, which is, if you want, the part of the analysis that I focused on in this slide. But also the other goal of the analysis was also to investigate the possible resonant diboson production. So. But I didn't cover this this part in my presentation because it was more about the Higgs self interaction properties. So I don't know if this sounds okay.
Do we have other questions from the audience? Yeah, okay. If not, we can move on to our next speaker. Next we are going to have Ramanpreet to give us a brief intro to himself and talk about the recent vector boson scattering measurements from CMS.
Hi, I'm Ramanpreet. I'm a graduate student at another university. These are the recent vector boson measurement from CMS. So I have presented the latest results that CMS has published, and we have measured inclusive and differential cross section for the VBS, and set some stringent limit on anomalous gauge coupling, that's it.
Okay, thanks for the nice summary. Do we have any questions from the audience? Okay.
Yeah, I had another question here.
Yeah, please go ahead.
I think it's on slide 13. We talked about including the EFT operators.
Okay.
Yeah. So did you consider any dimension 6 operators? Because there's a lot of trilinear gauge boson couplings that contribute to effective boson scattering, right? So the dimension 6 would creep in there.
Yeah, dimension 6, I think, yeah, as you said, is triple gauge coupling. We haven't considered in this channel right now, but the it's mostly the ZZ channel that targets that has that sets the limits on the triple gauge coupling. But I'm not sure if we have like the results are published for the triple gauge coupling yet with the recent data.
Yeah, it's just more of a question because the uncertainty in those triple gauge couplings will creep into the uncertainties on these dimension 8 here, right?
Right. Yeah, that's true. Yeah, I think that studies are going, but we will see that in coming probably within a year that we will have more more precise limits on these numbers.
Okay, thank you.
Yeah, thanks for the nice discussion. I don't see further questions. We can move on to our next speaker. Rosa Maria, would you please give a brief intro to yourself and the highlights of your talk?
Yes, okay. I am Rosa Maria Venditti from Bari University and INFN. It is in the south of Italy. And my talk is about the very first measurement of some of the Higgs boson coupling at a possible future muon collider experiment. I don't know if it's possible for me to share the slide. I tried, but not succeeded. Okay, thank you so much. Okay, you are projecting my slide, correct? Or
yes, our organizers are projecting your slides. You can tell us the number we should go to.
Okay. You can go to slide 3, for example, where you can see that at a muon collider experiment, the main production mechanism of the Higgs boson is WW fusion. And the goal of this very first work is to give an estimate of the sum of the Yukawa coupling of the Higgs boson with the B and C quark, as well and Z boson couplings. So in the next slide, you can see a sketch of let's say the very first preliminary detector design of this muon collider experiment. The futures of the muon collider experiment are, of course, the challenges are the muon production and also the beam-induced background that comes from the decay of the product of the muon that interacts with the material of the detector. And these generate a lot of particles that travels along the detector and complicates the event reconstruction. And in the talk by Nazar, you can find more about this. So in this particular talk, we try to give an estimate of some of the Higgs boson coupling, as I was saying. So first coupling we analyzed, if you go to next slide, is the Higgs boson coupling to the Z boson using the 4 muon final state. And I will go directly through to the result in slide 9. So we, for this first feasibility study, we adopted the very same Higgs analysis strategy adopted by the CMX experiment. And in the muon collider environment, with just this channel, we have been able to, let's say, to reach a 30% precision on this coupling, on the Higgs coupling to Z boson in the 1.5 TeV scenario that can be further reduced to 16%. So if you combine these results with all the leptonic final states, mainly muon and electrons, of the Z boson decay, you can reach actually the present precision of CMS and Atlas on this coupling of Higgs with the Z bosons. The other channel that we analyze, if you go to next slide, is the decay of the Z boson, of the Higgs boson into C quark. Next slide. The main background here are coming from the production of the Higgs to B quark and Higgs to gluons, and we developed a dedicated C-tagger discriminant using multivariate analysis in order to distinguish C-jet from B and light flavor jet. So if you go now to slide,
yeah. Sorry, Rosa Maria, this is supposed to be a very quick highlights, so please
okay,
wrap up.
Yes, yes. If you go to slide 14, there are the results. And okay, we have been able to reach the 5% precision here that is compatible to the results measured by click. So in the end, this is a very first preliminary study at a muon collider experiment, but shows compatible results with the one obtained by, let's say, the other facilities for future colliders.
Yeah. Thanks, Rosa Maria, for the nice talk and summary. Do we have any questions from the audience? And again, let me remind the panelists can directly unmute themselves and ask questions. So I have a question about this Higgs 2 ZZ24 leptons. I'm a bit surprised to see beam-induced background actually reduce your sensitivity by a certain amount, because I saw the beam-induced background are really soft. Why would that affect my ability to see those sort of energetic leptons from Higgs 2 4 lepton channels?
Yes, the reason is that actually the track reconstruction is not optimized in the presence of such a huge background. So even if some mitigation strategies for the beam-induced background are let's say, are under study, they are not yet have been implemented in the muon reconstruction. So let's say that the conformal tracking algorithm that we are using for the muon reconstruction is not optimized in presence of the BIB, and moreover, the BIB, let's say, mitigation is not yet completed. We should exploit still the full detector capabilities like the timing to reject this BIB. So these latest mitigation strategies have not been implemented in the software, so this is why the muon reconstruction gets so degraded when you include the beam-induced background effect. But this is under study, and of course will change in the near future once we will optimize the algorithm for the muon reconstruction.
Thanks for the comprehensive answer. Thank you. Okay, I think now we need to move on to our next speaker. Next, we have Samuel Lin to give us brief intro and the summary highlights of electric restoration at the LHC and beyond.
Hi, so yeah, I'm Sam from University of Kansas. I'm a graduate student here, and yeah, so we studied the electric restoration. We focused mostly on high LUMI and high energy LHC, and basically we measured the convergence of the Goldstone H cross sections for an electroweak restored phase to a standard model ZH and WH. And so we created a framework for doing this, and hopefully we'll be able to measure it soon. You're still muted, Jen.
Yeah, thanks, Sam, for the nice intro. Okay, I think we have a question. Oh, that's for a different person. We'll ask later. Okay. For Sam, do I have any question for Sam? Sam? Yeah. So, yeah. Okay. So we don't have a question right now. Okay, it's a paper we studied together, so
Yes.
I don't have a real question here either. Yeah, but yeah. But just can you briefly comment the beyond part of your study, right? You're saying electric restoration shall be checked at LHC and beyond. What are the beyond LHC components you are considering or planning?
So we're currently working on, as you know, the FCC and like 100 TeV collider. The idea is that you should be able to measure this better as you go higher in energy. And that's just because that's where the convergence happens. Yeah, so we're looking at 100 TeV colliders and also, high Lumi, high energy LHCs, like full results.
I see. Okay, thanks, Stan. Yeah, I don't see further questions. Maybe we can move on to our
question.
Oh, sure, please go ahead.
Okay. So hi, this is Ramona. So which kind of new physics do you have in mind when you want to probe this electroweak restoration?
So any sort of new physics that would affect the symmetry breaking in the standard model. So you could think of, if you maybe a composite Higgs model or anything like that. We're currently working on using SMEFT and HEFT to kind of take a model independent approach, but anything that would kind of mess with your electroweak symmetry or give you an electroweak symmetry or break your electroweak symmetry would be what you were looking for. Does that answer your question?
Yes, thanks.
Yeah. So yeah, I will abuse my panelist privilege here just to add to what Simon has said. I think the motivation for our study is really to bring up this angle of probing electric restoration from those processes, which can be mapped onto SMEFT or HEFT language. However, it's different. It's a particular direction in the SMEFT or HEFT EFT framework. In fact, it doesn't really need to necessarily follow this momentum expansion posture. That we can actually maybe in some sense closer to a series of operators specifically affecting this Goldstone equivalence direction, which is a combination of dimension 6, dimension 8, etc. We just feel beyond this momentum expansion EFT framework, this special angle, which is in very close connection to electric symmetry breaking, is an interesting point, an angle that requires special attention. Good. So now let's move on to our last speaker of this session, Tristan. Can you give a brief introduction to yourself and highlights of your talk?
Hi, yeah. So I'm Tristan from the Nikev Institute in Amsterdam. So I gave a talk about Higgs couplings to quarks and leptons with Atlas. So of course, for the third generation fermions, we already start to be quite precise, and we start to do differential measurements with SDXS and SMEFT interpretations. For Higgs and mu, of course, it starts to be close to be seen. But I also showed the new Higgs to CC result with charm tagging. So there's three highlights there. So first of all, we improved the world's best limit on the HCC signal strength. As a cross check, we also see a nice VW signal with one charm tag and a VZ signal with two charm tags, so from dye boson. And also we interpret our result for the first time in a direct constraint on the kappa C coupling modifier, where we put an upper limit of 8.5 times the value predicted in the standard model.
Yeah, thanks for the nice summary. Do we have any questions from the audience? Okay. Yeah, we don't have any so far. Let me begin with one. So it's very impressive for you to measure all those second generation Higgs couplings, right? Higgs to mu, Higgs to charm, right? Some of them are statistical limited, but it's not clear to me whether they're, whether we will improve a lot, right? I believe mu probably will improve a lot at high Lumi, but CC, is it the more dominant by my systematic uncertainties of my system? So are we going to improve dramatically at Halumi, or you think we are not going to do much there?
Of course, we're always going to improve.
Yeah, sure. I know we are. Yeah, but do we have a sense of? Yeah.
You're completely right. So the systematics are already quite tough. Of course, it's not a simple falling slope bump like in Higgs mu that we are looking for. So we have quite some systematics, and the main ones are from the background modeling currently. So from the V plus jets samples and the top samples, and also the limited statistics in the Monte Carlo samples, and also a bit on the flavor tagging. So especially on the sample generation, there is a lot to be learned. But I mean, something that we didn't. I mean, this analysis was quite complicated because also we use charm tagging, and there's not many analyses who use that. So we didn't exploit too much yet MVAs. So I think in the next version of this analysis, we will definitely make a big step again.
Okay, thanks for a nice answer. Let's see. Now we open the floor for a question for any speakers. If there are questions on Slack, or panelists have questions, or audience have questions, just directly type them.
Hi, Jean.
Yeah, hi.
If Luca's still here, Luca Franco.
Yeah. Yes.
I think it's slide 18 of his talk. The Higgs to gamma star gamma. LL. Yeah, my first question is, what's the difference between Higgs to gamma star gamma versus Higgs to Z gamma? Do you block out the Z pole in Higgs to gamma star gamma?
Okay, I will wait the screen to.
Yeah, I think it's 18.
Yes.
Yeah, so
okay,
for Higgs to gamma star gamma, do you block out the Z pole, or do you include the Z pole to the left with the leptons?
No, so basically these two results belong to two different analyses. So in one case where in the gamma star gamma channel, the signal, so the lepton pairs in the final state have usually a very low invariant mass. So this is in the end will result in very collimated energy deposits in our calorimeter. So this is, I think, the most important characteristic. And this is, so for this search, we had this year the first evidence. So we reach 3 sigma. So the other is a different, the Z gamma channel was targeted by a different analysis. So we were looking for a peak in the Z gamma final state. So so in this case, we didn't reach the evidence yet. So
yeah, I had another question about this too. So thanks for your answer. But if I look on the right-hand plot, basically the bottom part of it, I don't really see an excess of 125 GeV. So when you quote this 2.2 significance, is that for the specific mass point that you've already measured for the Higgs?
Sorry, can you repeat the last part?
When you quote the 2.2 significance for H to Z gamma, is that specifically for the Higgs mass of 125? Because if I look at this plot, I don't really see an excess right there at all.
Yeah, so this is for the so 2.2 sigma is over the background only hypothesis, right? And yeah, this is for NIGS at 125 GeV.
Okay.
So
Okay. Good. Thank you.
Yeah, thanks for the discussion. We have a question for Tristan. Maybe it's naive. Is that how about the Higgs-2 strange? Is that feasible at the LC?
So yeah, I mean, define feasible. I mean, we can always try to search for it, and yeah, my impression is people are starting to look into strange tagging, and I think it's in view of also trying to do Higgs-2 SS bar. I have also seen that people looking in it for future colliders, but I think at Atlas and CMS, people are also starting to look at it. So, I mean, Higgs-2 CC is tough. Higgs-2 SS is tough. Electron Yukawa is tough, but that's why we do this, right? So we should just try it.
Yeah. Do you know I mean, briefly what? Yeah.
And a bit the historical perspective. I mean, I think 5 years ago, people said that Higgs-2 CC bar was hopeless. You know, I mean, they really thought that that it would be kind of impossible. Whereas now we set a limit of 8.5 times the value on the Kappa charm. So I think it shouldn't discourage people from trying it.
Yeah. But do you know briefly how what's our strategy for SS? How are we tagging S? Or how are we planning to tag S?
Oh, I don't know if there's any official things on that yet. So I don't know. But I mean, you can try something, right, to identify strange.
Yeah. Okay. Do we have other questions for any of the panelists? Okay. Yeah, I don't see any, and you know, our session already lasts longer than planned. And I just want to thank everyone for participating in this panel discussion and for you know, nice progress and reports you made. You can continue a discussion on the Slack channel, and we will reconvene at 10:30 Central Time. Okay,